we started off talking about electrostatics. In electrostatics, we have electric charges, and they're basically just sitting still. And so this gave us the idea of electric fields, and then we started talking about electric potential. We did mention, however, that there is some such thing as electric current, and that's the rate of change of charge. So if you have a bunch of charges in motion, then that gives you electric current. And so that's our definition of current is charges in motion. So clearly the unit is going to be coulomb per second. So a coulomb per second, and that is an ampere. Okay. We sometimes just abbreviate that as an amp, and the symbol is A, so that's a coulomb per second. And so this is our basic definition of electric current. Now, because charges are conserved, current is conserved. Now, because charges are conserved, then electric current is also conserved. So, for example, let's say that you have an electric circuit, and so you got a fuse box or electrical panel, you got a wire going off, and you've got several electrical outlets, and you've got several things plugged in here. Okay, so if this object over here is using 2 amps, that means there's 2 amps of current running through there. If this is using 3 amps, then that means there has to be 5 amps running to there, 3 amps going this way, 2 amps that way. And this is using 6 amps, that means that we have a total of 11 amps going in here. So the currents are going to add in this fashion. So that means we have conservation of charge. So at every junction, then the current into the junction has to equal the current out of the junction. And this turns out to be a junction rule that we're going to use later on. That current into a junction, so you have a junction, you get a wire going in here, and then you got 2 wires coming out. And if we call this I1, and that's I2, and that's I3, then I1 has to equal I2 plus I3. So current in has to equal current out. And so we'll be using this concept quite a bit later on. Well, in discussing electrical current, we also realize that if we got a wire or something, okay, now we know in electrostatics that all the charges end up on the surface. But in electrodynamics, where they're all moving, you can actually have current going through the middle of the wire. Okay, and so this is not quite the same. And so you would, for example, you would have a conductor, and we create an electric field in the conductor, and so what happens is that charges will flow. Okay, well, again, we define charge flow as positive charge flow. So if you have a bunch of electrons, if all the electrons are going to the left, that means the current is to the right. Okay, and so because the current is defined to be positive charge flow. And this is actually something that's been confusing me as a student when I first started learning electricity, and that was you look at a battery, and so we have a battery, we have positive terminal, negative terminal, and we connect something across here, then we say that current is flowing that way from positive to negative, but what's really happening is electrons are flowing out of the negative terminal into the positive terminal. So the direction of flow is going to be exactly backwards of the actual things that are flowing. So when we're talking about electric current going through something, then we also realize that it's impacting the object it's going through. If we get electric charges moving through here, they're bumping off of the atoms that are already in there. The charges don't really just go straight through because there's atoms in the way. So they bounce off of the atoms. So what happens is you get an electric field this way to the right, and so you have all these atoms in here, and the electrons or the charges or whatever, they're moving along, and they'll bounce off of an atom, and they bounce off of atoms. Then the recoil of bouncing off actually causes that atom to move and vibrate. The result is that when you have electric current going through a conductor, you're actually having the electrons bounce off the atoms, causing those atoms to vibrate. Well, the more the atoms vibrate, the hotter the conductor gets. So you actually have heat generated with current flowing through something. Well, clearly, the more electrons that flow through there, the more impacts they're going to be. But if we had a bigger diameter, then what would happen is that the same number of electrons would be flowing through there, but you'd be spreading out the effect of them running into things. And so it would have less of a deleterious effect on things. So we define something called the current density. The current density, we use the symbol J for current density, and the current density is essentially defined to be I over A, where A is the cross-sectional area. So that means that the current density would have units of amps per square meter. Okay, so current density. Now, we also define current density as having a vector quantity. So if the electric current is that way, we would say the current density is that way. And so what we do is we would then step backwards and say, well, in that case, the cross-sectional area has we would say the area has a vector in that direction. So I would be integral J dot dA. Okay. Now, that would take into account the possibility that the current density is different at different radii there. Now, for what we're going to be doing for our class is we're going to pretty much assume that the current density is uniform across the area for the most part, in which case this just becomes J times A. Okay, and that gets us back to the J equals I over A. All right, now, so this gives us our basic definition of current density. Now, next thing we're going to do is we're going to introduce what's happening at the microscopic level and explain how all this works. So far, we've been talking about this largely in a macroscopic realm. That, yeah, we've got the electrons moving, we got charges moving and so forth, but we don't really see those because there's so many of them moving. Imagine how many electrons are moving in 1 amp of current. It's a huge number. So the next step is to look at the microscopic level, and then we'll start looking at doing examples.